This is our last lesson for Unit 1, and in this particular lesson, we are going to talk about parent functions and their transformations. So along the upcoming lessons, we're going to be talking about the different kinds of functions that might exist. So we're going to start with some basic parent functions, and as we go along, you'll see that the transformations remain the same, the idea remains the same, and how we approach them also remain the same. So before we begin, pause the video and take a look at some of these parent functions. Most of them you will recognize. However, we won't be covering all of them in college algebra, but most of them we will see. Let's start with vertical shifting. So regardless of the function, if we add k to both the function itself, so the function, then we add k to it, the graph will either shift up if we are adding k, or it will shift down that amount of units if we are subtracting k from the function itself. Our first example is if f of x is equal to x, find f of x when we add 2 to it. So we are adding 2 units to our function. This is going to tell us that we're going up 2 units from our parent function where it would start. So in my original function, if I had the point 0, 0, if I'm shifting my graph up 2 units, that's going to affect the y value. Which means that in f of x plus 2, the same point 0, 0 would now be 0, 2. So in my picture in Desmos, I graphed f of x equals x, and then I graphed f of x plus 2. My red line is the original parent function of f of x, and my purple line here is the function when I added 2 units to that function. I see in my original point 0, 0, the same point with the translated function, that point now becomes 0, 2. And every single point on my original function line is shifted up exactly 2 units. Sometimes we want to have a horizontal shift, and notice that this horizontal shift happens inside the function, not outside the function. So if inside the function I am adding h, be careful because that means I'm going left that many units. And if I am subtracting h, that means I'm actually going right that many units. So if we are adding or subtracting inside the function itself, we need to go left or right, and it's almost opposite of where you think it might be going. So we still have f of x, and now we're going to add 2 inside the function. So again, adding 2 is inside the function. And if I'm inside the function and I'm adding 2, that means I'm going to go left. So if I'm going left on the graph, that is going to affect my x value by subtracting 2 units, so I need to go to the left. So in my original equation, if I had f of x, we started with the point 0, 0, and if I'm going left 2 units, again, that's affecting my x value, so I'm now going to be at negative 2, 0, will be my f of x plus 2. In my picture here, again, I still have my red line is f of x, and my purple line is f of x plus 2. Noticing that that is the same appearing transformation as f of x and then adding 2 because they're a linear line. But ideally, when I'm looking at my point here, in my original equation, I'm shifting it to the left 2 units. And that is true with every point. But notice that is the same thing as if I were to shift my graph up 2 units. Because we know these graphs go in both directions forever and ever, the transformation of x plus 2 and f of x plus 2 are the same transformation, gives the same ending result, only because it's a linear function. It won't happen with every single graph, just in this particular one that happens. So I wanted to make sure that was clear, that something you might have seen as we were graphing. Sometimes we would like to reflect our graphs across the x-axis, or we might want to reflect them across the y-axis. So if there is a negative sign in front of the function, that means we're going to reflect across the x-axis. And how we do that is our y-coordinates need to be multiplied by -1. If we have the negative inside our function, we're reflecting the graph across the y-axis, and that means that we'll be taking our x-coordinates, multiplying those by -1. And we'll see that in action in the bottom. So noticing on the left-hand side, our graph is being multiplied by the negative on the outside of the function. So that means that we're going to reflect across the x-axis, and our y-coordinates are affected. Our original function here is f of x. Let's say I have this point 2, 2. Since it tells us that we multiply the y-coordinates by -1, and we're reflecting across the x-axis, my new point for negative f of x, this point is to -2 because it's affecting my y-coordinates. However, if I have the negative on the inside of the function, this is going to affect our x value for this example here. So again, I have my original function of f of x. Let's still use that point, that point 2, 2. And again, this is affecting my x values because I'm reflecting across the y-axis. So now my point f of -x, its point is -2, 2. Since it's affecting, I multiplied my x values by -1 since I went across the y-axis. We also might want to do some vertical scaling. So vertical scaling means vertically, so we're going up and down. This is going to affect the y-coordinates. So we're going up and down. So if we want to stretch upwards and stretch downwards or shrink it downwards, this is going to affect our y-coordinates. And what will happen comes from multiplying the outside of a function by a specific number. Depending upon that specific number, if that number is greater than 1, we're going to vertically stretch, so we're going to get bigger, and that's going to affect our y values by a factor of a. So factor we know means to multiply, so we'll multiply our y values by that whole number. However, if we have a fraction, so if our number is less than 1 but greater than 0, we are going to shrink. We're going to get smaller. So we will multiply our y-coordinates by 1 over whatever that number is. So in this particular example, my red line is still f of x. Let's still say I have 2, 2 here. and we want to take a vertical scalar of 2. So currently 2 is greater than 1, so we're going to follow this bullet point. That means that we are going to take our y values and multiply by 2. So this is a vertical stretch. So we're going to get taller. Our original function, we had the value of 2, 2. We need to multiply our x value by 2, our y value by 2 to get a larger y value. So we multiplied, just to make a little note here, our y value by 2 so that we can stretch it larger. So here this point is at 2, 4 for 2 times our function. We also can scale horizontally. So we can stretch it horizontally or we can shrink it and make it tiny. This number comes in from the inside of our function. This is going, since we are stretching horizontally, this is going to affect if we're going to stretch left and right or shrink left or right. So if the value inside the function is a fraction, so it's less than 1 but greater than 0, we are going to horizontally stretch. We're going to horizontally stretch by a factor of 1 over b. So again, we're going to multiply those x coordinates by 1 over whatever that value is. However, if b is greater than 1, that means we're going to horizontally shrink, and we're going to multiply those x coordinates by whatever b is. So we see in our original function, here's f of x, the red line staying consistent here. Still have, let's do the point, this time 1, 1. Okay. I noticed that inside I have a factor of 0.5 or 5 tenths. So 0.5 is less than 1 but greater than 0. So our b is 0.5. So we need a factor of 1 over 0.5. So this is 2. So 1 divided by half is 2. Therefore, we're going to multiply our factor. We'll multiply our x values by 2, 1 over b. So in our original function, we used the point 1, 1. And in our new translated, we're doing half of x. So if I multiply our x value by 2, we'll have 2, 1. So I see that we're stretching out since our new value is 2, 1. So we're stretching it out horizontally. So we went in the right direction. Now, of course, we are able to do all of these transformations. You don't just do one at a time, right? So it is possible that we could be translating left or right, up and down. We also could be vertically stretching or horizontally stretching. We could do all of these pieces in one function that we are given. So let's suppose we have a function g of x where we have a number in front of the function, we have a value in front of the x inside of the function, adding another value, and then adding the end at the very end. There is a specific order we need to complete these. So we need to either shift our graph left or right first. Then we need to do the reflection and horizontal scaling next. So we need to work on B second. Then we need to do the vertical scaling as well as reflection across the x-axis third. And then the very last thing is almost the easiest part, is shifting up or down. So order matters. Follow these in this specific order, and then they follow the pattern here as well. So we have to follow the pattern. So let's see this in action when we have a bunch of different transformations happening all at one time. First, I need to identify what my parent function is. So it's asking us to explain how the parent function can be transformed to obtain the following: 1 minus the square root of x plus 3 over 2. Well, I see the square root, so I know that my parent function has to be the square root of x. Just the plain old square root of x is going to be our parent function. So off to the right-hand side, I have just the parent function graphed in red. So this is the parent function. So let's start building this and see what might happen. I'm also going to rewrite the function that is given so that it looks like f of b of x plus h plus k, so I can identify what we're doing. So to rewrite this, I'm going to say that this is the same as f of x is equal to the opposite of the square root of x plus 3 over 2, and then put my plus 1 on the outside. Because notice we have the plus items off to the right-hand side. I'm then going to separate this fraction into two fractions such that I have the opposite of x over 2 plus 3 halves plus 1. So we're getting a little bit closer. And then finally, I'm going to bring this half in front of the x to make it a little easier to look at. So this is the same as the opposite of the square root of 1/2 x plus 3 halves plus 1. So now it looks just like our a times f of b of x plus h, plus k, plus h plus k. So when I'm looking at the connection between the two, my k value is the 1. My h value is this 3 halves. My b value is the 1/2. And then my a value is this -1. So I'm not going to necessarily be scaling vertically, but I definitely am going to be reflecting across the x-axis. And the order in which we complete this is to focus on this part first, right? Because this is first in our list. So from my parent function, I'm going to shift my graph left 3 halves of a unit. So I'm just going to focus on this part here, x plus 3 halves, as we build the transformation on the right-hand side. So notice in my graph here, I'm going to shift the graph 3 halves units left. So this is affecting my x value. So as I look at this point 0, 0, I'll have -3 halves 0, which was shifted 0, 0 left 3 halves. This is going to be my new starting point when I look at part 2. So part 2 is going to be the 1/2 in front of x. So we'll do that part next from our starting point. So on this next slide, I have the starting point with my new red line of x plus 3 halves underneath the square root. And now I need to look at from here, from where we left off, what comes next. So what comes next is putting in the addition of the 1/2 x plus 3 halves. Well, this value here tells me that I'm going to horizontally stretch because this is between 0 and 1. So this is my b value, and 1 over b is 1 over half, which is 2. This is going to vertically stretch my graph because my x values are going to be multiplied by 2. So when I look at this, where our original piece, and if I multiply my x value by 2, negative 3/2 times 2 is negative 3. So my point here, horizontally stretched by a factor of 2, and I am now at 3. Everything else will also be shifted to the left as well. If we take each and every one of these x values, multiply by 2, the y values would remain the same. So the only thing that changed was the x value was multiplied by 2, and our y values remained the same. The next step, once we've done that, is to look at the negative in front of our equation. So to go from where we left off here, the next step is to look at the number in front of the function. And although we don't have any number, we do have a negative. This negative tells us that we're going to reflect across the x-axis. And this is going to affect our y values. So we're going to multiply our y values by negative 1. So here is my, where we left off. And here is where we're going. Notice that every single y value became its opposite, while our x values remained the same. So my x value of negative 3, 0 remains the same. However, 0 and 1.225, notice as it's reflecting across the x-axis, becomes its opposite. So the same is true for every single point. So this is where we are leaving off. We have one more step though, because we have the plus 1 portion, the k part. So this is where we left off on the last slide. Let's add in the last step by adding 1 to the equation. So here is where we left off. So it looked like I got rid of everything else, no sense in keeping everything else, but I need to add 1. So I have f of x. We've done the opposite of, we've done the half, x plus 3/2. And now we need to do this last part of add 1. This tells me that I'm shifting my graph up 1 unit. Shifting up tells me I'm going to add 1 unit to each y value. And I know you can't see it, only gives you so many characters to see in Desmos when you graph it. So notice each one of my y values when paired with its x value is shifted up 1 unit. So each one of these, our y value has moved up 1 unit. And that does pair with their corresponding values from where we left off. So putting it all together, on the bottom here, we first started at f of x equals the square root of x. This was our parent function. And I knew it was my parent function just because it had that square root, so I knew where I needed to start from the front page. Then we shifted our graph left 3/2 units. Then we had a horizontal stretch. By a factor of 2. Then our third step, we reflected across the x-axis. And finally, step 4, we shifted up 1 unit, where we got to our new function of negative square roots half x plus 3 halves plus 1, which was the black line there. In this next example, it's asking us to use the absolute value parent function, which is f of x, of the absolute value of x, to find a formula whose graph is obtained in a sequence of transformations. So it's giving us what transformations, and now we have to build the graph. So it's asking us to shift left 3 units, vertically stretch by a factor of 2, and then shift down 4 units. So I've got the generic equation here that we need to take a look at first. So shifting left is the h portion, and h is what happens first, so we'll take care of that first. Vertically stretching happens third, because that is our a. And then shifting down 4 units is our k, and that happens fourth. So notice we don't have a horizontal stretch, so we don't have a step 2. It didn't tell us. It only has 3 of the 4 options. So the first thing we need to do is shift left 3 units. So in order to shift left from our parent function, shifting left means that has to happen on the inside of the function and the opposite sign of which we believe it should be intuitively. So I need to shift it left 3 units, and I can also check this using Desmos. Since I put this absolute value of x plus 3, I see here's my parent function, and I do see that my graph is shifted left 3 units. If I would have accidentally put x minus 3, I would have been way over here, and that would have been a right shift, and you would have known right away that's not right. So from here, we don't have a step 2, go to step 3. We need to vertically stretch by a factor of 2. So vertically stretching by a factor of 2 is not too bad, because in order to stretch by a factor of 2 vertically, our b has to simply be the same. We don't need to worry about a fraction because it's vertically stretching, since a is greater than 1. And in this case, a has to be 2 for a vertical stretch. So by putting in the equation where we left off, now putting in that vertical stretch, we know that vertically stretching, if I were to start at this particular point here, negative 2, 1, vertically stretching is affecting our y value by multiplying it by 2 for a vertical stretch. I see here's my parent function, my shifted, and now when I'm looking at negative 2, 1, multiplying my y values, I do see it's getting skinnier because I'm trying to stretch my my shifted left graph. I'm trying to stretch that higher. And then the last portion from where we left off with the vertical stretch, our last step is to shift down 4 units. So notice I'm shifting down 4 units by including the negative 4 at the end of my function. So all of my points now after the vertical stretch are being shifted down 4 units. So I see that that is subtracting 4 units from each of my y values when my x values remain the same. So putting it all together on this last page so we can see all of the transformations step by step. I put the parent function here. We shifted left 3 units. We then vertically stretched, and then we had a vertical shift downward in this particular instance, so it does look skinnier. So again, working those steps from start to finish, 1, 2, 3, 4, one at a time, using graphing technology to help you, will be key to helping determine whether or not you're going in the right direction and it makes sense in the context with which it's asking you.